Great. Yeah, thank you, Ken. Really appreciate it. And good morning, everyone. For both the people online and people in the seminar room. Today I will talk about a kind of a already happening reality. As we're witnessing the quickly entering of the agentic AI into our transport systems and the broader society. So I'm going to talk about the implications and how we could evaluate and optimize decisions in this or the system level decisions in this new era. So if we look at the more like a canonical view of transportation systems, there's usually people talk about the five big modes, right? That's the roadways, railways, waterways, airways, and conduits and pipelines. The roadway and railway, waterway, and airway, the four were for mostly for transporting people, goods, and water, right? And a little bit energy as well. And then the conduits and pipelines are mostly for transporting energy and information. Um, it's just but recently there was also like Hyperloop and other new innovative modes of transportation that is really blurred the line, right? People now using conduits and pipeline for transportation purposes as well. But no matter what, those are the five major modes. But I would here propose that another very useful way, especially in the era of AI, is to look at it from a human machine perspective. If we really think about it, humans have been inventing and utilizing machines for transportation purposes for a long time, right? Since the invention of the wheel. It's just so we can look at this the phenomena of people, the movement of people and goods and energy uh, from the interaction of the human machines through the infrastructure with in the background of the natural and built environment. So not only just for the machine here is not only for particular vehicles, but also the broader life cycle oriented machines that are helping to make the transportation happens, like the planning tools, computers, smartphones, as well as the survey equipment and the construction equipment for the pavement those and dozers and all those major aspect, as well as computers that are used for control the traffic. So there's a narrow sense of machines in transportation, that's basically vehicles and the delivery robots. But there's also broad way of defining machines in transportation. I mostly am here in this talk and talk about the broader sense, right? So not just the vehicles. It's just so we're calling it human machine transportation systems or HMTS. It's just right now in addition to the humans, now the machine used to be a passive tool and now become more and more passive. So it becomes very interesting to see this kind of the previously the human using machine inventing using machines now is more like a dance, right, between humans and machines. And if you look at the history a little bit of the past, like a century or so, we see this every new inventions like automobile, the novel pavement materials, all the way to the new business models like Uber and Lyft, and then later on the autonomous driving, and as well as the disruptive events like COVID, there's really fundamentally influencing how people travel and then their preferences. And then the electrification is another big one recently. And then in the past few years, there have been like major boosts in transportation research on using generative AI for various purposes of transportation planning and management. But we're entering right now a new era of agentic AI, where broadly speaking, it can be defined as the AI systems that exhibit a certain level of agency. But agency, I'm here talking about five major dimensions. That's the capacity for one is goal formation and then interpretation, that's goal related. And then the strategic actions or the strategic planning and actions. And then the third one is social engagement with humans and other machines using natural language. And then the fourth one is the strategic use of external tools and resources. And the fifth one is the self-reflection and learning. Um, So this is the major. Some people say 4 or 6, but I would say 5 is probably a good balance of understanding what's the agency. Right? So the term agency has a really deep philosophical and psychological root, and I here highly recommend the Professor Albert Bandura's work called Agentic Foundation for Social Cognitive Theory. I think it's a really good way of kind of looking at what we mean by agent or agency, as well as the what do we mean by the adjective, like the agentic, what we mean by that from the psychological perspective. I think it's very helpful, but there's also some very important literature, seminal literature in philosophy. But this term is brought into the technology side around 2024 by Andrew Nguyen, who's a former professor at Stanford. And then he proposed to use the agentic AI to kind of settle a debate. Right now, previously in 2023, 2024, people are arguing whether a system or AI system is an agent. Right. So he argues that instead of arguing about this, we simply just call it they are all agentic, right? And we should focus on how to make it more and more agentic and make this human-centered. So this is a big shift actually from generative AI to agentic AI. The generative AI focusing more on essentially a passive model, right? A reactive model where we give the prompt input, and then the system will give us some sort of contents like the text or image or videos. But agentic AI actually proactively take actions. So in fact, the term agent it's come from I believe it's a Latin word. Literally means actions with purpose. So the agent is actually taking actions proactively and to influence the environment to achieve a particular goal. That goal can be set by the agent itself or by the external sources. Um, so I think I want to clarify here the difference between agency and autonomy, just to further, as a comparison to further clarify agency, right? So on one hand, we have this low agency, low autonomy situation. That's this typical machines, like very, very passive tools, ranging from like regular hammers all the way to like manual driven cars. At the same time, we have now already observing automated executors or execution machines, right? So like we can see the REM in the sense is the automated machine. It doesn't really reason, right? It doesn't go. We have a pre-programmed rules for it to automate the whole process without external control. That can be as small as a robotic vacuum cleaner where I can specify the particular route and then it will clean the room, all the way to the REM or even more automated programs. And at the same time, we have this very high agency case with low autonomy that can be like a very sophisticated chatbot, for example. It doesn't really take any actions, but it gives suggestions and it can reason in a very sophisticated manner. But lastly, we have this possible future, not really future right now. It's already happening. It's a machine that it can be digital or physical, right? Digital or physical machine that is both high in autonomy and high in agency. That will be, the machine that can set its own goals or interpret the goals that can be highly ambiguous. But the machine can actually interpret it to break it down into tasks and then execute them to realize what's the sequence of the task and how to achieve the goal. And we already see there's two strategies of achieving this, right? On one hand, we see people who are like for example, Waymo, right? They have an automated car, and then now they're adding the working with Google. Well, technically they're Google, but they're working with Google and then adding Gemini and other agentic systems architecture to make the Waymo can talk with people, can reason, and can address ethical conditions, ethically challenging dilemmas, right? On the other hand, we see all of the companies that they're focusing more on having a machine to have agency first, and then gradually make it a lot of tasks to be executed autonomously without external control or like human input. So there's both are the working trajectory that we are right now witnessing in the industry. And speaking of industry, if you look at you search the Google, you see like agentic AI plus transportation or some other industry, you see a lot of news, like ranging in transportation at least. You can see the agentic AI has been already incorporated in one or another, with or without human in the loop, to for the formal transportation planning and policy making. And we'll see, including Montreal, they're adding AI agents for monitoring the construction sites and for potentially even adding AI agents into the construction robots for maybe speed up the construction process, road maintenance projects, and lower the cost. And another major aspect is the last two, which is the adding AI agents into the cars, and for mobility services, and as well as adding AIs into the delivery robots. That's for more like for the logistics. So if we kind of agree on this, to see that accept the fact that it's already entering our transportation systems, we can already envision the near future, where we have a network of AI agents, which they may be interacting and hopefully collaborating, but maybe like not collaborating, right? Maybe fight with each other, argue with each other, negotiate. But no matter what, we can see them as a network. On the one hand, they can serve the illicit demand needs and provide information to the human users, as well as they can serve the broader technical and non-technical stakeholders that can be like policymakers, engineers, planners, managers, operators, and politicians. On the other hand, those AI agents actually serve as a buffer between the human and then the mobility services, where the AI agents actually can help us design and operate the actual mobility services. That can be transit services, the fleets, or even like airlines or some other particular services that using the infrastructure. And we can even think about it even more broadly, where the AI agents can actually not only providing service by assuming the infrastructure is already there, but also actually can think long term and plan, design, construct, and maintain the actual physical infrastructure that provide foundation for the private and the public mobility services. But of course, the overall goal here is we're hoping the private and public mobility services can actually be human-centered, that can serve the system users as the travelers, residents, both the general public as well as the vulnerable populations. And then in this particular sense, we're calling this overall framework as Agentic Human Machine Transportation Systems, or Agentic HMTS, or AHMTS. And then I'm calling this particular part where we have AI agents kind of interacting, have this control loop with the actual transportation systems. I'm calling the Agentic Transport Systems, or AgTS or ATS. So I think this is already a component view of the future HMTS. And here, to be even more specific, I want to mention 4 concrete examples that my lab and my collaborators are working on. And of course, I'm also looking for open for even broader collaborations. And if you're interested, please reach out to me. One is right now we're focusing on is the use of AI agents for understanding the market, right? Conducting the surveys and interviews, eliciting opinions and preferences from the general public, from the and as well as the technical stakeholders. And then we're developing agentic systems for the planning and the management of the infrastructure asset. So left side is more like for a little bit like understanding the demand, right, about the transportation market. And the right is the understanding or the management of the actual physical supply infrastructure. And for the operation side, we are proposing this concept of vehicle agency or agentic vehicles, with mainly through a collaboration with the University of Luxembourg, and as well as the people in McGill. And then right now I'm expanding this to Polytechnic and HEC. But when we're putting all those agentic vehicles into a fleet, and there's additional more opportunities and implications. And then when those fleets are involved or in the company generating the traffic that is also has other non-agentic vehicles that can also have implications for both opportunities and risks for both control and management. So as to quickly dig slightly deeper into this, the example one is the agentic vehicles. Well, we already see the companies are where the car manufacturers and the technology companies are collaborating. Like for example, a few months ago, Qualcomm and Google are working together on adding the Gemini models directly into the vehicles. So the vehicle, even in the countryside, there is no internet connection. The vehicle can still reason and think. And then they can provide as what they call it the agentic experience of traveling. And then another company, Sanhang, they're focusing particularly on using AI agents for self-assessment, right? That will be kind of understanding the battery conditions, engine situation, and then when they need to, and then they can explain this to the drivers, that's manual-driven cars, so that's drivers. And then when they need, they might directly make an appointment to the auto shop or the auto repair. So I think in Montreal, a lot of people kind of struggle on going to the auto shop for changing the tires twice a year. So in this case, maybe the vehicle will check your calendar and notice, oh, in the next 2 days you're not using it, so the car will automatically make a appointment and then drive itself to the auto shop to change the tire and come back. So it's a kind of a avoid 4 trips basically, right? Because you need to change the tire twice, and then so you can save a lot of the time. But also you can also arrange its also charging needs and filling needs based on your calendar information or your additional request. And Tensor and Lyft right now they're collaborating on. Tensor is the first company that actually call their car agentic vehicle or agentic car. And then they are right now working with Lyft. I think they're thinking about having this in the future shared agentic vehicles that are as a competition with Waymo potentially. But it's a kind of a potentially new mode. It could be interesting because they can interact with the passengers in natural language, which is at least Waymo right now they don't have. And also they can talk with the pedestrians and the other people around the cars to ensure a more safe and smoother travel experience for not only the passenger inside, but also the people involved interacting with the vehicles. So here you can check out our paper recently accepted by Jiangbo ITS conference. But here I'm just showing you some possible core capabilities of agentic vehicles with one concrete example. So where people have a heart attack, the autonomous vehicles might still go into the destination, while the agentic vehicle might actually reason this and know you cannot respond. They will make change your destination to the hospital and make a and call 911 or something in advance. And another concept we're proposing is this potential trajectory of developing the agency gradually increasing from 0 to a higher level. And then the agentic vehicle can actually serve as a particular active participant in the future. And the second example is like the natural progression. We'll have a set of individual agentic vehicles that form a fleet where we can provide agentic mobility services. And then, but also they have implications on the generated hybrid traffic where we have both agentic vehicle and non-agentic vehicles. So in the agentic HMATS, this line becomes the central control and the distributed control might be blurred, which can be a source of opportunity to make the transportation systems more adaptive and resilient. But the risk is the local agentic decisions that create a system level inefficiency. So that's the quick second example that we're working on using agentic AI for controlling we're operating the overall traffic fleet, the vehicle fleet, as well as the overall traffic. And the example 3 is the the use of the agentic AI for demand forecasting, modeling and forecasting, and data collection. So we are using AI agents for both collecting active data, like using surveys and interviews through chatbot, as well as they can decide what sensor data they can collect from and then process the data, clean it up, and then they can model human behaviors and for both the actual system users as well as the technical and non-technical stakeholders. So on the left, we are right now particularly using AI agents for conducting surveys and interviews on understanding people's travel preferences and mobility needs and how they respond to unseen technologies in terms of their daily routines and behaviors. And then on the right hand, we're creating those digital avatars using agentic AI, and then so can mimic people's behaviors, and then so we can run simulation instead of actually testing certain alternatives, policies. We actually can ask people's opinions, and then let them actually play out and how this new transit route or new policy, congestion pricing, actually going to affect the overall transportation system in terms of the energy consumptions, emissions, travel time, etc. And then the fourth example of using agentic AI is to use it for helping the transportation planning agencies for taking actions on influencing the urban transportation systems, and then they can collect the information about the performance of the current systems, and then they can make a better decision using a particular policy pie. So when we have this agent, the set of agents that are helping the policymakers, we have this hybrid network of AI, a human and AI network, and then they can actually serve people better. And we're right now working with California for this, but I'm hoping that we can work more with the regions in Canada and Quebec. So these four examples actually differ in scales and the horizon, but for example, the agentic vehicles operate over seconds, over second meters, and then the agentic mobility services also work in minutes and over the whole network. Agentic demand modeling operates over days, months, or scenarios, and behavioral adaptation. Agentic infrastructure planning operate over years, budgets, and institutions, communities. But they are sharing the same structure. And a set of AI agents observes a certain systems, updates the internal state representation, selects actions and use tools, and communicates with human and other agents, changes the environment, affect the future observation. Right? So the four examples also show that agentic HMTS is not simply a new application domain of AI. It changes the nature of the transportation decision-making or the overall system dynamics. Right? In conventional transportation analysis, we often evaluate the model, algorithm, or policy by asking whether it improves the specific components, forecast accuracy, route efficiency, traffic signal, vehicle assignment, etc., and pavement condition prediction, and investment prioritization. And in HMTS, decision support tools becomes a couple decision systems. They observe, infer, act, communicate, revise, and influence the overall transportation condition. A demand forecasting agent may say alter the demand it predicts. So it's really tricky when you predict something, but you wanted it to be useful. But when it's actually used, your prediction is wrong. Right? So it's there's this chicken egg problem that is really tricky. This is not just for the prediction of the demand, but also for any other decision that when you have a decision support tool that is actually endogenous as an endogenous component in the system, right? So there's system level. So there's a component level risks, right? The agentic system might fail through perception errors, model misspecification, bias data hallucination, reward misalignment with the human value, and cybersecurity vulnerabilities and privacy breaches. At the same time, we have the system level risks, the risks that are more subtle, but it's probably more detrimental. Each component may appear locally competent, but the couple system may behave poorly. Navigation agents may collectively shift congestion into a residential area, and then the vehicle agents may overload charging stations. Forecasting agents may create self-fulfilling service reduction, And the planning agents may reinforce long-term investment bias by repeatedly favoring data-rich areas. And the risk is even higher when we couple the agency with autonomy. So we need a evaluation tool that can capture the dynamics, uncertainty, and those potential both at the component level risk and the system level risk. And the evaluation can and then be further used for optimize the agentic systems design and the overall translation system dynamics, right? So as a recap, we talked about I talked about the concept of human machine translation systems, HMTS, and then the new era of agentic HMTS. And I gave 4 examples, and then I talk about the need of rigorous evaluation tools for the dynamics. So this is the longest part. The rest part is faster, I promise. So the part for the part two, since we already mentioned it, if we look at all the possible options that can actually for us to use as a potential tool candidates, then really the natural answer is Markov decision process, MDP, and it's associated with the extension, which is the partially observable MDP, and then the state space representation or state space models in the control theory, right? Because they are all have the similar kind of the observe, infer, act, system respond, evaluate, and update kind of feedback loops. So this is actually a very natural starting point, and we can just examine whether it's actually a good candidate. And if not, how we can modify it or augment this to make it more suitable, right? And then because of this GERAD talk, I kind of just assume that we're all familiar with MDP. So just quick mentioning that is the kind of can be think about as five element tuple. We have a system state, action space, transitioning map of from one system state to the next, from one time step to the next time step, right? And we have a discounting factor to consider the future reward. And we have the immediate reward function, R. And a policy is the state is a mapping from the current system state to the action. So that's the kind of a canonical view of this. So and we can optimize this by defining a particular objective function J, and we can actually calculate the cumulative reward with or without discount factors. And we can use the Bellman's equation for updating to come up with the value function for describing each system state. And if we let a particular decision agent to maximize using the policy about maximizing the value, then we can achieve a optimal MDP, right, where the agent is actually taking the optimal decision. But MDP itself is just descriptive. But I think it's helpful to think already in the optimization manner. And we have the POMDP, partially observable, where we're extending this to not to assume that the decision maker can observe the system state correctly and perfectly. So in this case, we need the observation space, and we need the observation probability, a mapping from the system state to the observation system state space to the observation state space, right? And then it has this POMDP has a great connection, almost mathematically the same, to the state space representation, where the control people usually use X to represent system state. So we can describe this as a system state for the next time step using the difference equation. We have the system state plus the U, which is the input, and the noises and the parameters. And then we can the observations, which is Y, they call it output. So the POMDP is automatically assumed. And then we can further adding the belief state estimation based on the historical information H, and then we can find out the corresponding mapping of the stochastic mapping to the current system state. So we have the mapping of this belief. So the POMDP actually emphasize on mathematically they're essentially the same, but the POMDP emphasize decision making under uncertainty, while the state space representation emphasize the dynamic feedback and the stability. So, but I believe the agentic HMTS need both, and then we need to think about this in both manner, from like kind of operations research perspective of POMDP and the control perspective of emphasizing the feedback control. And a sufficient large POMDP can represent almost anything, right? But it doesn't mean it's helpful. So unstructured augmentation may become too large to compute, and too vague to estimate, and too difficult to interpret, and then disconnected from the governance. So the principle is we do not simply make the POMDP larger, we make it structured. So a useful augmentation should specify what can change, who or what may be change it, and how fast it may change, and under what constraints, and how the consequences will be evaluated. So as a recap, the MDP slash POMDP slash state space representation for evaluation is it's a really great starting point for us. And then, but it seems that right now for the complicated agentic AI era, it's a little bit insufficient, and we need a more structured augmentation for it to adapt to the newer reality. So in comes to the part 3, and we are right now exploring mostly with my postdocs, Ali Islami, and a few other PhD students and my collaborators on figuring out how to augment this. So here is just an example where we're augmenting the state space in a structured manner, so to consider more explicitly of the physical operating system state, the human social behavior state, and then machine memory state, machine states, and the tool output system state, the external tool system state. And then the similar idea principle applies to the action space, where we dissect, decompose the system action space into roughly 5 components, where we have the operating, the physical action, the information acquisition, communication actions, right, different from the actual physical movement. And we have the tool use actions, and we have the governance approval or escalation actions. So that can be like one way to differentiate or categorize different types of actions that the agents may take. In here, the agent can be a human agent or a machine agent. And then I think that here I also want to highlight the very important part of that's different than the POMDP, or at least it's not implicit, not explicit. That is the agentic AI system can change its own objective or reward function. So we need to, so basically the reward function becomes the endogenous component of our system. So we need to capture this idea that priorities may change with system conditions, human feedback, emergency status, institutional rules, or agentic interpretation. So in this case, we have roughly 2 major ways of doing this. One is we make the reward function endogenous component. Another is we have a set of reward functions, and each one has associated weights, which is called in here is lambda. So we basically augment the previous cumulative reward function or the gaining function by putting a weight lambda into the cumulative reward function with or without discount factors. And then, but the lambda itself is actually endogenous, even though the R itself is a traditional reward function. So that can be one possibility. So this captures the idea, this examples captures the idea that the priorities may change with system condition and human feedback and emergent status, institutional rules, and agentic interpretation. However, objective adaptation must be distinguished from the objective authorization. And AI agents may recommend changing priorities, but human operators, agencies, public agencies, regulators, or predefined protocols may need to authorize that change. This is where the governance becomes part of the model. The governance is represented through the authority states, admissible action sets, constraints, and the escalation rules. So this framework prevents, so by having this structured augmentation, this framework prevents agentic HMTS from becoming an uncontrolled everything model, right? Where every agent is connected with everything without any management structure. So by doing this explicitly on knowing what kind of agents they are, human agents, machine agents, and where they belong to, which the organization, and what's their constraints, and which subset of agents they can talk with, we actually can start thinking about how how the communication really happens in the system, and who should talk to whom and who should not talk to whom. Okay? And then right now, I mean, like we have this problem in our reality. It's really hard to control, right? The human planners, like say in ARTM, in after the work, after 5 p.m. they might have a 5% with the people in the operation. They will talk about work, and then those things will influence subconsciously or unconsciously or subconsciously, indirectly and then directly. So it becomes actually very hard, challenging to manage. But in the future, where the agent, especially the machine agents, can actually talk with each other in a more documented, traceable manner, then we can actually start managing this. So that's this part 3, where we have the examples of architecture of a structured and POMDP of augmentation, and I talked a little bit of the governance implications. And lastly, I want to just the structured one I just mentioned about the augmentation examples give us a high level architecture, but we still need a more concrete examples, I believe, in this talk. So I'll just kind of quickly mention a work I'm working with my postdoc Ali Islami on this idea of having the vehicle fleets and infrastructure all evolve under inputs, disturbance, and control policy. So that's kind of a control view of POMDP, right, in the era of agentic AI for transportation systems. For these systems, traditionally, it was control engineers who designed the controller, certify stability, and implement it. Any parameter change was rule-based and pre-approved. The engineers was always in the loop. And now with agentic AI, it is AI agents doing this, tuning gains, switching controller architectures, modify control objectives, all can happen when the system is actually running, which is true. We can't really stop transportation systems. It's always running on the safety critical systems like a vehicle operation, as well as the multi-billion-dollar infrastructure planning process, right? And this raises the fundamental question: when the agent is one modifying the control architecture, does the closed loop system remain stable? So this is kind of the basically what I just talked about in section 3, 2, and 3. But more like from using the control language to say this. To formalize this, let us define the system and the agent operating on it. The physical system evolves according to nonlinear dynamics, where X is the system state, U is the control input, W captures the external disturbances, the output Y is the what we can measure, but the agent does not act on Y alone. It acts on the information state I, which aggregates sensor observations, its own memory, outputs from external tools, and interaction signals from the human and other agents. This is the key difference from classical control. The agents has the richer context-dependent view of the world, and this is what we formalize here. You see, so the agentic control law formalizes what we described in the first slide of this section. The control input U is generated by the policy pi of the alpha of t, which is the controller architecture. It acts on the delayed version of the information state, where tau captures the delay introduced by the inference for the 2U's for the reasoning process. The parameter theta allows runtime tuning of the gain. Theta encodes the current control objective. So each of this alpha, theta, zeta corresponds directly to one of the agentic capabilities from one of the 5 agentic capabilities. To make this concrete, we think of the vehicle switching its driving strategy, a fleet invoking an optimization tool, a demand model revising its forecasting workflow, and an architecture manager modifying its project prioritization logic. In this case, the agent is not just changing the control output, it's changing the mapping that's generating it. And that is what makes a stability analysis non-trivial in this case. So I don't know whether it's helpful, but for some people, if you're aware of system dynamics paradigm or the causal loop diagram, then here is the explanation. And then I know for some of you, maybe I'll make it even worse. but at least for some people who are visual thinker, I think it could be helpful of what I just talked about. So basically, we have a original control system where the control input and exogenous disturbances and the system state itself will influence the dynamic of the system, right? At the same time, the system state and the external disturbances influence the actual observation, right, of the system state, the state output. And then, but at the same time, we can call this overall information state. It's a collection of observation, system output, memory, the inputs from the human and other agents, because they're not autonomous, they need external inputs, and then plus the external tool or outputs, Z, and the memory itself from the agents, human agents or machine agents. It's actually can obtain information from the observation in the past, the human and the other machine agents inputs, the external tools as well. And the external tool itself is actually influenced by the the computational configuration, right, capabilities. It might have some certain delays through the computation and the computation. And then the computation delay plus the information state is actually from the Go descriptor where we can describe as a long list probably where each word each agent's goal is for at the present moment, which is dynamic and endogenously changing. And then we have this information state that it actually potentially influence the control parameter, and the parameter itself is actually influencing itself, right? So that's kind of the tricky part where the parameter is actually changing, where you can say we have a hyperparameter that are actually governing the control parameter. And lastly, we have the goal descriptions plus the control parameter, which is actually the serving as the overall parameter for influencing the control input U under certain policy. That actually it's more like a meta policy. So the agentic control law formalizes what we described in the first slide of this section. The control input. Oh, sorry, I talk about this. So once we have this understanding about what do we mean by endogenous control policy and the inputs and the system dynamics overall. So one thing is we need to really talk about is the stability, right? And then we're proposing this concept of a stability budget. So each agentic capability introduces a cost itself, right? Agentic capability of the 5 introduces cost against this baseline, whatever that baseline is, like say non-agentic system, right? The baseline stability margin gamma comes from the spectrum special properties of the closed loop system without any agentic modifications. Specifically, it is a decay rate of the system when the controller is fixed and no adaptation, switching, or delay is present. Then each agentic capability, such as parameter adaptation, delay, and controller switching, each introduces a stability cost, reducing the stability margin. And these costs are not independent. They jointly consume the same margin of the overall system. Then the stability budget, lambda, is what remains after subtracting all of this cost from the baseline margin. When the lambda is greater than 0, stability is guaranteed. Otherwise, we cannot ensure stability. One interesting finding is that we find that if we have 2 separate controllers, both of them are stable, will cause the system to be stable. But if we switch them relatively fast, we actually can cause the instability of the overall system, even though both of them are actually good controls. This gives us a practical design criteria. Before deploying an agentic controller, compute lambda and check whether the system's agentic capability fit within the available stability margin becomes actually a very important checker. So this simulation here shows a key insight from the stability budget. We consider a switching nonlinear system time delay system, a simple one, with 2 individually stable modes and an adapter parameter. Since delay and switching both consume both same margin, either one of them could push the system into instability. For example, if the delay in generating the control signal is large, the agent needs to wait longer before it can switch the controller. So if the switch is too frequent and too fast, the budget is exhausted and its stability can no longer be certified. So the same logic applies to the parameter tuning. The more aggressive the agent adapts, the less room there is for switching or delay. This is what we mean by the stability cost to be coupled with the overall system. The second simulation tests all three mechanisms simultaneously. The adaptation, switching, and delay. The stable use case, the case uses a long dwell time, a small delay, and a low adaptation rate. This gives a positive lambda and the state convergence to the origin. That the unstable use cases uses a short dwell time, a larger delay, and a faster adaptation rate. This gives the negative lambda and the state diverges as it becomes unstable. But using the mentioned stability budget, we can actually predict which configuration is stable and which is not, and when to actually intervene the system. So in recap, the final section, so we demonstrate a concrete control-oriented interpretation of agency. Basically, is the change of the control architecture in runtime. And we talk about embedding agentic capabilities into the unified system state space representation. And we talk about adding agentic AI changes the induced closed loop dynamics. And we propose the concept of stability budget and use it to show how it can be useful for governing the case where we have AI agents that are actually control the system. So as a summary, so I talk about agentic AI is rapidly entering our transport systems, regardless whether we want it or not. And I propose that we need to really guide the development and the deployment of agentic AI to ensure our transportation system remain human-centered, even though the agentic era is already started and planning agencies and the operators are already using AI agents. But I think at least we can catch up and then just propose a more sophisticated, rigorous guidance for making sure that human HMTS is actually human-centered. And I mentioned the MDP family models and the state-space representation actually give us a really good, useful tool for this, but it does need some sort of augmentation in a structured manner. And then to ensure it's not only evaluating the different policies in the future, but also potentially even optimize the agentic AI systems that is in transportation systems. And lastly, I gave a concrete control-oriented instantiation of the augmentation principles. And then I argue the need with my postdoc Ali Islami, the need for stability budget concept to govern the agentic transportation systems. So just a one-liner, so we should evaluate not only what agents do in our transportation systems, but also what their agency does to the overall transportation systems. So the goal here is to build agentic HMTS, whose agency is mathematically represented, dynamically evaluated, institutionally authorized, and socially accountable. So that's pretty much it. Thank you, Messi. So there's I really appreciate all the funding sources I got through this process, and then the support, especially NSERC and the exploration fund, NFRF exploration fund, and the FRQ. And then I got a lot of help from other faculty members. And then on the right side, you can check out some of our publications related to this topic. Thank you. And please reach out to me if you are interested. Here is my email at the bottom. So thank you.